Good afternoon, everyone. And yeah, my name is Travor, and I'm currently a first-year undergraduate student studying mathematics at Yale. And today my topic is bounded gaps. And like before everything, let me introduce certain notations that are used throughout the talk. Yeah, so this is just some like analysis stuff. So in analysis one, we're told that every convergent real sequence is bounded. The opposite is not true. However, we can define if the sequence is bounded, it's going to have a limit supremum and a limit infimum. And the limit supremum is given by this symbol, and the limit infimum is the other one. And there are also some other notations for that, but I'm going to use this one because it's quite complex. And if the limit supremum of a sequence an equals to u, then for every epsilon, we can find sufficiently large n such that all of them are less than u plus epsilon. But on the other hand, like for every epsilon greater than 0, we can also find infinitely many n such that the sequence an is greater than u minus epsilon. And some examples that can be expressed using limit supremum and limit infimum are shown below. Like suppose we consider the sequence -1 to the nth power, then it equals to 1 infinitely many times, and equals to -1 infinitely many times. This indicates that the limit infimum of the sequence is -1 and the limit supremum is 1. And we can also use this notation to express certain results concerning the gaps between primes. Because example 2 and 3, every prime numbers, they are at least 2 units apart from each other. This indicates that Pn plus 1 minus Pn, where Pn denotes the nth prime, then this difference will always be greater than or equal to 2. And if we can make this inequality an equality for infinitely many n, then we will be able to show that there are infinitely many consecutive primes that are exactly 2 units apart, which is equivalent to the twin prime conjecture. And for the second one, it indicates that we can make prime gap arbitrarily large. So that's why the limit supremum of this sequence is positive infinity. So these are just some notation, and this is the ingredients that will be covered in this talk. So first we'll be going to introduce like what prime gap is and what are some current results on this line of research. And I'll introduce Selberg's Sieve, the Sieve of Goldston, Pintz, and Yıldırım, and work of the Chinese mathematician Yitang, and also James Maynard's work, who became a Fields medalist this year. And all of these works are very relevant to the study of prime gap. So let's start with the introduction. Like before bounded gaps between primes became a thing, mathematicians call the study on prime gaps, especially making concerning the small gaps. They are concerned with the small gaps between primes. So for brevity, we use Gn to denote the difference between consecutive primes. So this is called a prime gap function. And from the prime number theorem, the limits infimum of Gn divided by log of Pn is less than or equal to 1. This indicates that there is a constant such that Gn is less than that constant multiplied by log of Pn infinitely many times. So this means that a Gn will be smaller than a logarithm, will be dominated by a logarithm infinitely many times. And on the other side, Gn is also greater than logarithm infinitely many times. So this is actually giving a two-sided result. And this part, like any line of work dedicated to improving this part, will be classified into a study of small gaps between primes. And any attempt on improving the right-hand side of this inequality will be classified as a study of large gaps between primes. And bounded gaps between primes is a belongs to the area of small gap between primes, which is what I am about to introduce. And so this is the result given by the prime number theorem itself. It gives an inequality that is less than or equal to 1. And Paul Ehrlich, well, he actually made a lot of contributions to many different areas in mathematics, and some of them are in number theory. And this is one of his contributions. He shows that this limit infimum cannot be 1. So it has so there certainly exists some constant delta greater than 0, such that this limit infimum is dominated by 1 minus delta. And later on, mathematicians begin calculating some explicit values for the delta. And in 2009, these three people they unconditionally proves that this limit infimum equals to 0. But that is not their most important contribution. In 2009, the same year, the same research paper, similar methods, we proved that under a certain hypothesis regarding the distribution of prime numbers in arithmetic progressions, we can make the prime gap, the gap between consecutive primes, bounded by some constant infinitely many times. Suppose there's a number n, and we can find infinitely many positive integers n such that this function gn is going to be less than n. And this is kind of like a approximation towards the twin prime conjecture. If we can make n down to 3, then we have the twin prime. And so that's a conditional result. And this is the one I am going to introduce later as well. And later in 2013, the Chinese mathematician Zhang Yitang, he modified the work of these three people, the G, P, and Y. He modified the work of GPY's method. He modified the method of GPY and then shows that we can make Gn smaller than 70 million infinitely many times. And I will also explain why he obtained 70 million instead of any larger number. And after Zhang Yitang, so this is his paper was announced in in summer of 2013. And James Maynard uploaded his paper to archive in winter. It's only 3 months apart. And James Maynard said that, okay, we can make this less than or equal to 600 infinitely many times. And after James Maynard, people began optimizing this bound as well, and then make it down to 246. And this is just very crazy. And also there's also a little bit symbols on the right hand side. It means that for any integer m, we can make the difference between Pn plus n minus Pn bounded infinitely many times, which means that we can find some large numbers such that we can squeeze in arbitrary number of primes in this range infinitely many times. And this is a generalization of the prime gap itself. And the tools that are used to derive all those results are called a Sieve method. And I'm going to introduce what a Sieve method is in the context of analytic number. Sieve theory. And this is a quote from a Sieve theory textbook by Henrik Iwaniak. He happened to be the person who reviews the paper of Zhang Yitang. He's the reviewer of Zhang Yitang's paper. And he said that we often apply, consciously or not, some kind of Sieve procedure whenever the subject of investigation is not directly recognizable. So when we're confronted with something that we don't know, we tend to divide them into different cases and then analyze them respectively. And in the case of prime numbers, in order to discover those prime numbers, we need to remove numbers that are known to be certain multiple of some numbers. So suppose we have a range of 1 to 100, and to obtain primes, we remove all multiples of 2 except for 2 itself, and then all multiples of 3, and then so on. And this is the Sieve of Eratosthenes, and yeah, and the modern Sieve methods are built upon this idea. And these are some results that are obtained using Sieve methods. We introduced this omega function, which is quite standard in number theory. It denotes the number of prime factors of n counted with multiplicities. For example, 4 is 2 times 2 because it's got 2 prime factors. It got 2 in its decomposition. As a result, omega of 4 equals to 2, and omega of 12 will be equal to 3. We count the repetition. And so using this notation, we can conveniently summarize the result that are obtained using Sieve theory. In 1919, Viggo Braun, he was basically the first person to study sieves analytically. And using this method, he proves that the reciprocal sum of all twin primes, they actually converges. But you do the sum over the reciprocal of all natural numbers, it diverges. But for twin primes, they converges. But for primes themselves, they diverges. So this means that the twin primes are much rarer than prime numbers. But still, it doesn't really mean that there aren't any. So the convergence of this reciprocal sum doesn't mean that we only have finitely many twin primes. For instance, there are infinitely many square numbers, but the reciprocal sum of the square numbers converges, and it converges to pi squared over 6, a really interesting result. So this is Viggo Braun, and later on, adapting Braun's method, Lev Schneerman, who's a Soviet mathematician, he proved that every natural number is a sum of bounded number of primes. So we can find some absolute constants, and then ensure that every natural number is a sum of primes. It is a sum of less than or equal to C, no more than C primes. And this letter C, there originally it was a few, I think it was originally a few 100,000, and then this constant is later on reduced to 27. So this is the line of work about Schneerman. And here comes another Chinese mathematician. In 1973, Chen Jingren, he proved that for every large even integer n, we can find some prime such that n minus p is composed of no more than 2 prime factors. So in brief, especially in China, we have a word the 1 + 2 proposition corresponds to that result. That every large even integer is a sum of a prime and a product of at most 2 primes. So this is Chen's theorem. And in 1978, Henrik Iwaniec, the same person who said this quote, he proved that we can find infinitely many integers such that n squared plus 1 is either a prime or a product of 2 primes. This is very close to the conjecture that we can generate infinitely many primes using that expression. So these are some quite classical results in Sieve theory. And we are going to so these are some results regarding Sieve theory, and now we need to see what is Sieve is. So we go to the concrete part. So what is a Sieve? So from an abstract starting point, we just suppose that A is just some subset of integers, and Z is some integer that is greater than or equal to 2. The reason for that is because 2 is the smallest prime number. And when this function S denotes the cardinality or the number of elements of this set. So the set is described by taking an element of A that does not have any prime divisors less than Z. So we will define the size of the sets to be the Sieve function, and this is the notation that is quite standard in analytical number theory. And this function satisfies 2 basic properties. The first one is monotonicity. If we make Z large, then we can only have a smaller number of elements remaining in this new set, because we are removing numbers that are multiples of primes. And if we remove more primes, then there will be less elements remaining in the set. And also, like it's also motivated. Like suppose we have a number, and this number do not have small prime divisors, then it is possible for us to restrict the number of divisors of this number. An example would be like suppose like n is an integer. If we are able to show that this integer does not have any prime that are less than or equal to the square root of itself, then this number must be a prime. Like so let me let me introduce this argument very quick. So suppose it has like more than one prime. Like suppose n is equal to like p1 times p2. And because we know that those prime divisors must be greater than square root of them, then we see that if we just multiply them together, we get a number that is greater than them, which is a contradiction. And this argument can also be generalized. Suppose that we have an integer n such that all of its prime divisors are greater than like say like n to the 1/3 power. Then it is going to have no more than 2 primes in its decomposition, because otherwise we will get some number that are greater. So using this idea, we can set some appropriate z. Like suppose all the elements of the set is less than x, then we can make a z to be certain power of x to ensure that the prime number of prime factors in each of the elements of the set A is bounded by a certain controllable quantity. And this is why sieves are important in the study, because if we can just make the right-hand side down to 1, we can produce prime numbers. And here are some examples. And so you don't have to like remember this for this talk, but like if you're interested in the sieve theory, it's likely that you will be seeing this kind of examples in the text or in lectures. So when we set up the set n like this, we can obtain a sieve that is suitable to study the representation of integers as sum of 2 primes or 2 like almost primes, the Goldston problem. And if we set up A like this, then we can use this function to study the twin primes. And this inequality is essentially giving a upper bound to the number of twin primes less than or equal to x. And this is the starting point where Brown proves the reciprocal sum of twin prime numbers converges. And these are two they are quite like something like 100 years ago. It was like in the early 20th century. So this is what a sieve is. And yeah. And there are sieves that allow us to deduce certain lower bounds, and there are ones that allow us to obtain upper bounds. And for our purpose, we will introduce one certain sieve that gives an upper bound, but that upper bound is strong enough that we can even use that upper bound to study some problems concerning lower bounds, namely the bounded gap between primes. And so let me introduce this mathematician. He came from Norway, and Viggo Brown also came from Norway, and his name is pronounced as Atle Selberg. And he has some major, so these are some of his major achievements in the first half of 20th century. So in 1942, he proves that if we consider all the non-trivial zeros of the Riemann zeta function, the function of emerging in the Riemann hypothesis, then there is a positive probability that you will find such a non-trivial zero located on the critical line, on the line where a Riemann conjecture that all non-trivial zeros should lie on. And in 1947, Selberg introduced Selberg's sieve. He called it like lambda squared sieve, because in most kind of tools, you don't really just name something new after yourself by your own paper. And so this is what he did in 1947, and I will introduce this later. And he also produced an elementary proof of the prime number theorem in 1949. By elementary, in this context, I mean that we don't use any methods from complex variables. So it doesn't really mean it's like relatively easy. Like in fact, by comparison, it turns out that using the proof of the prime number theorem, using complex variable methods, turn out to be easier than the elementary proof. But this remarkable achievement, combined with the previous two, allowed him to receive a Fields Medal in 1950. And he also made a lot of remarkable contributions in the second half of the 20th century. So that's why I put some thoughts here. So let's have a look at the Travor student. And so we mentioned before that this function is essentially counting the elements of the set A that are free of prime divisors less than Z. Which means that if we let this capital P denote the products of all primes less than P, then this function is counting the number of elements of set A that are co-prime through this product capital P. Because otherwise, it's going to have a prime divisor that is less than. And this is also true like vice versa if we reverse the logical equation and expression. And so this is this parenthesis is just the shorthand for greatest common divisor, and by co-prime I just mean that the greatest common divisor is 1. And so Selberg constructed the sequence. This is a sequence of real numbers, and satisfies that when D equals 1, the sequence equals to 1. So if we look at this square term, when A and capital T are co-prime, this is going to be 1. And this vertical line denotes the symbol that D divides some number. And if this is 1, we're only going to be summing over lambda 1 in this square term. So in this case, we have a strict equality. But when A and P of D is not co-prime, it's going to be summing over some terms that are other than lambda 1 that are not yet determined. However, because we are squaring it, it's going to be some non-negative number. And that's why we have an inequality on this side. As a result, as long as we can pick some lambdas satisfying these two conditions, then we will obtain an upper bound for the Sieve function. And this is actually quite flexible because we can apply certain optimization techniques to choose a least upper bound for this quantity. And we will be going to presenting a sketch of that optimization. And before doing that, so set AD denotes the set of multiples of D in the set A. This is just a shorthand notation, and this part follows from a standard but technical interchanging of the order of summation, which I'm not going to show it here. But so the result is this, and this bracket just denotes the least common the least common multiple of these two integers. And so in order to expand the right-hand side, we need to obtain certain estimates for the size of the set AD. And by plugging in certain concrete examples, we see that in most cases, we can find some function G of D such that this set is roughly, the size of the set is roughly G of D multiplied by X, and X is just some positive real numbers. And if we just take A to be the set of integers less than X, then this quantity will be approximately the size of X over D. So in this case, GD is equal to 1 over D. And 1 over D is a multiplicative function. Multiplicative, I mean, suppose G is multiplicative, then if A and B are co-prime to each other, then G of A times G of B is exactly G of A times B. So in a general context, we assume that the size of the set can be well approximated by a multiplicative function G of D multiplied by some real number X. And R of D will be used to denote the error in the approximation. So plugging in this hypothesis, we'll obtain this expression. So S will be less than or equal to X times some term plus some error terms. So M will be that will be the shape of the main term, which is quite similar to what we got here. And E will be the error term. And to obtain the error term, we also have an additional condition imposed on the sequence lambda. So this lambda, we want to say that like lambda D will be 0 if D is very large. And like suppose like D is larger than the letter R. As a result, the error terms can be transformed into this expression. And like in between, there's also a series of technical operations about interchange in the order of summation. And lambda max is just the maximum amount of the absolute value of this sequence. And omega, so we introduced the capital omega function before, and this time we are talking about the lowercase omega. In capital omega, we count prime factors with repetitions, but here we just count the distinct prime factors. Suppose 12 is like 2 squared times 3, then the capital omega gives 3, but this lowercase omega gives 2 because it only has 2 distinct prime divisors. So this is the shape of the error term of the Selberg's upper bound scheme. And this shape of error term will also appear when we are facing the problem of prime gap. Yeah, so this sum, like it is a multiplication of 2 variables together, like 2 lambdas multiplied together. So we can say that the order, or the degree of this term is 2, which means that the main term denoted by capital M is a quadratic form. And like in middle school, we mentioned about like conic section, those are also quadratic forms because they are considered they are consisted of like some x squared and y squared. Those are also quadratic forms, and we encounter quadratic forms here as well. And usually, like we are summing over like 2 different lambdas here, but we hope that we can sum over the square of certain same terms together, so that the sum can be handled easier. Because like if the term inside the summation is squared, then the sum is going to be non-negative, and it will be better for us to manipulate the sum. However, we only restrict lambda to be some real sequences. So this means that it can be negative, which is not convenient for us to manipulate, to deal with. As a result, we perform a transformation. And that transformation also involves a series of technical number theoretic calculations. And here's the result. So if we just introduce this function, h function, this is also a multiplicative function, but when d is a prime number, it satisfies that relationship with the function g. And then somehow using the properties of multiplicative function, we see that the reciprocal of g is like the reciprocal is like has a relationship with the reciprocal sum of the function h. And this is summing over the divisors or positive divisors of d. And if we define this h function and then perform a transformation on lambda, we transform lambda into y, then the main term will be a sum over some non-negative number, which is perfect for our purpose because we are only summing non-negative numbers here, and this thing will be more convenient for us to play with. Yeah, like if you are really into this field, you see those sums, you are just saying that okay, we will play with it. And using a certain inversion method, the Mobius inversion, we can recover lambda from this new variable y, the diagonalized parameter. This means that if we choose some y, we can also determine lambda. And if we choose some lambda, we can also pick some y. So there's like a bijection between these two functions. And this is like you don't have to like remember all of these like throughout the talk. It's just some results that are like in the progress, like some part of Okay, so we have diagonalized the main term, and now we apply a kind of Cauchy's inequality to obtain the optimal main term. So by so this is like by squaring this term. Like if we were to look back at this lambda formula here, if we set d equals 1, then this term is going to be 1 because we have assumed that lambda 1 equals to 1. And this is going to be mu of m, and this term doesn't need to exist because this is just enforcing that m is a multiple of d, but d equals 1. So like every integer is a multiple of 1, so we don't have to worry about this term. Which means that the sum inside equals to 1. And if we square this term, the sum actually becomes a can be applied to we can apply some Cauchy-Schwarz inequality to give an upper bound for the sum. And one term in the right-hand side of the inequality turns out to be the main term, and the other term turns out to be some new sum over a certain function. And by like picking y carefully, we see that this inequality becomes an equality if we were to choose ym in this form. And this is like the division symbol, like this on the denominator. And by plugging this giant monster into the Mobius inversion formula, we'll obtain a even more monstrous quantity. However, we don't have to like work with this quantity in prime guess. So they will look nicer in the next few slides. So let's see. So to obtain a nicer form of that lambda d expression, we need to impose more hypotheses on G of d. So we consider the specific case when d is a prime number. So we want to find some k such that G of p is well approximated by k over p when so we have this assumption, and we also hope that so k is also a positive number. It is not necessarily an integer, but for our purpose, we are considering the case where it's a positive integer. And this k will be called the Sieve dimension. And for example, in the twin prime case, so A of D is counting the set of multiples of like D in this of this element. And when D is a prime, we see that n times n plus 2 is divisible by prime if and only if n is either divisible by prime itself or n plus 2 is divisible by primes itself. And this actually, so this congruence is actually giving two solutions when prime is not even, when prime is greater than 2. And after a certain analysis, we see that this properties allow us to conclude that G of P is well approximated by 2 over P when P is large. And this allows us to conclude that the twin prime problem, if we set up the sieve like this, we get a 2-dimensional sieve. And this fifth dimension will be very interesting because what James Maynard did is a kind of dimensionality reduction attack. And we will go over that in a few slides. So under this assumption, like this G of P depends on K, which means, and because H is also a function of depending on G, and lambda D is a function that is related to H and G, or hence G itself. As a result, this optimal lambda is also something that depends on K, and also this letter R and D. And by plugging these properties into this monster, it becomes something that is relatively beautiful. It's a so this is like an estimation. It's an asymptotic expression to the optimal form of lambda, which means that if we plug in this equation 2 instead of this this gigantic equation 1 into the Selberg sieve, we will produce some results that are equivalently optimal. So we can work with this one in the future, but not this one. And yeah, so that's the asymptotic formula for lambda. And that's like everything about Selberg sieve. So we can like finish up on this section and move on. And the next section is that about lower bounds. We talk about Selberg Sieve, and all these optimizations are dedicated to finding a least upper bound for a certain quantity. But here, we also, like in the case of prime gaps, where we need to do with lower bound problems. And in this few slides, I will talk about how we can use those results we obtained previously to study lower bounds. And a typical lower bound problem is that A and B are two subsets of integers. And we hope that the intersection of these two sets are not empty. So when A is equal to this set, so 2n is an even number, and minus p or p denotes a prime number. P always denotes a prime number here. And if we make this capital B is denote the set of all primes. If A and B have intersection, have non-empty intersection, then we can see that this even integer can be expressed as a sum of two primes. So this becomes a lower bound problem on and particularly the Goldbach's problem. And when A is the set characterized by p plus 2, where p less than x is a prime number, then the intersection of A and B will be the set of twin primes less than x. And if the intersection is going to increase with respect to x, then we can obtain that there are infinitely many twin primes. So this lower bound problem corresponds to the twin prime conjecture. Yeah, this is a set, but this set depends on x. Yeah, and we are considering the size of their intersection, which also turns out to be some quantity that depends on x.
Yeah, we can show that it's increasing.
Yeah, if we can show that it's increasing, we have to twin prime the conjecture. But like currently, like we don't have that. But we know that it is, we know some of its upper bounds. And in small theoretic situations, it's easy to obtain upper bounds, but not lower bounds. And that's why Chen Yıldırım result is just kind of surprising, like, to everyone. So, and including Chen's theorem, mathematicians in the 20th century, they study lower bound problems by performing certain inequality where x is just certain quantity and then minus a series of y quantities here. And to obtain a lower bound for the left-hand side, we need to obtain lower bound for x and upper bound for y. But in the past, this lower bound x is obtained using some more traditional Sieve methods, the methods of Brown and all other Sieves that are called combinatorial Sieves. They produce lower bounds, but their lower bounds are quite ineffective. Their lower bounds are relatively ineffective compared to the modern methods. And the term yj will be approximated by the Selberg Sieve because we can deal with some upper bounds here. And Selberg Sieve is a very effective method to estimate upper bound. And this is the traditional method. And now we can introduce a modern method. It's called a weighted Selberg Sieve. So in the traditional case, we see that this inequality allows us to give a lower estimate of the number of elements in the intersection. But if we don't care about how many elements are in the intersection, we can do it more directly. And this direct approach allows us to show that the intersection is non-empty. And which is sufficient for our purpose because, like, for Goldbach's problem, we don't have to know like how many primes satisfy this property, but as long as we can find one, that will be enough. We just need to show that it's non-zero. And here's a direct approach for that. So we define a weight function. So this weight function is the map some elements of set A we defined before to real numbers. And we force this function to be non-positive when the element is not when the element of A is not an element of B. And then we consider this summation because the square term doesn't really change the sign of the summand. However, if we sum over everything in the set A, and S is a positive number, then we can find at least one element of A that allows us to make this W of M positive because the whole sum is positive, and W of n is a real number, and this thing doesn't change its sign. So this whole sum being positive means that we can find at least one element of A to make this term positive. And to make this positive means that we have an intersection with the set B. And this is the approach that is taken by GPY, these three mathematicians, and I'm going to introduce that later in a few slides. So here's some more words. Because in Selberg's we can apply some nice Cauchy-Schwarz inequality to obtain a precise form of the optimal lambda in the parameter. However, here we don't really, because like the optimization problem depends on the shape of this wave function. We cannot really choose some lambda like as we did before. As a result, we just pick the function randomly and then see like we can get s greater than 0. And by randomly, like any function. However, we have motivations here. So we can choose this function in a motivated fashion. So we don't have to iterate all possible functions. Like, although in this situation, we can't really talk about some subdimension, but using certain informal heuristics, we can still tell that like this lower bound problem has a certain dimension. So suppose this lower bound is like a k-dimensional problem. Then we can just plug in the lambda we obtained here. This lambda is optimal for a k-dimensional sieve in the upper bound situation. And we just plug this right-hand side expression into the equation 4. So that, and then we just expand all the summation and then play with those multiple sums and obtain something interesting. So that's the, yeah, so that's the idea for this form of like a lower bound problem using weighted Selberg. So now we can introduce the work of GPY. And in the specific area of research, their work is called the GPY sieve because, well, that's the first letters of their names. So these are the pictures of these three mathematicians. And yeah, so yeah, we can like see how their sieve is, what the sieve is. But before like presenting the precise form of the GPY sieve, we start with some motivations. So we let H denotes a set like a subset of a finite subset of integers composed of k elements, and we call it a k tuple because it's a tuple and it has k elements, so it's a k tuple. And we call this admissible if n plus h1, n plus h2 up to n plus hk do not have fixed prime divisor, because otherwise this function, those integers can only generate composite numbers, or just can only generate finitely many prime numbers, because when n is large, n plus h1, n plus h2 up to n plus hk will always be some multiple of certain primes. Any questions? Okay.
That's what do you mean by fixed prime divisor?
Yeah, so fixed prime divisor means that suppose like it's always divisible by 2. Then n plus h1, then if we make n arbitrarily large, it's still going to produce numbers that are divisible by 2. And these are even numbers, they are not prime numbers. And the restriction that the admissible condition that we impose here is to present a certain conjecture. That's if we can make, if H is admissible, then n plus h1, n plus h2, and up to n plus hk are primes simultaneously for infinitely many n. So this is a conjecture, and this condition is a necessary condition for this conjecture. And this conjecture just said that this is also a sufficient condition. And we can also make this. We can also present this admissibility condition more formally. Suppose we have a polynomial defined by n plus h1 multiplied up to n plus hk. And for a concurrence equation modulo P, if this polynomial has P roots, then it's not going to be admissible because this means that the prime P will be a fixed prime divisor of this polynomial. As a result, if we let this one, the symbol, this nu of P, denotes the number of zeros, number of roots in this concurrence equation, then we want to ensure that the number of roots in this concurrence equation is strictly less than P, or otherwise it's going to have a fixed prime divisor. And this polynomial will also be appearing in the GPY suit and the work of James Maynard. And yeah, this is the conjecture. So this is the prime K couples. So GPY's motivation actually came from this prime K couples. We can current technology doesn't allow us to prove the conjecture itself. However, it is possible that if we choose some fixed given admissible H, and then we can ensure that at least two of the quantities, at least like for every n, like we can find infinitely many integer n, such that we can find two numbers I and j, such that n plus hi and n plus hj are prime numbers. This, like, in other words, we are saying that this couple can generate at least two prime numbers. This will allow us to show that, like, there's a concept such that the gap between consecutive primes is less than that constant infinitely many times. So because we choose hi and hj are different, and we just iterate all possible differences between elements of the tuple H, then the maximum of these differences will be an upper bound for the limit infimum of the prime gap. So that's so from this motivation, we can set up the lower bound problem. So in this case, we want to find so this n such that there are at least two primes generated by the tuple, and we can perform. So as a result, we can develop this weight function, and this function chi is essentially the characteristic for prime numbers. When n is a prime, it's equal to 1. When it's not a prime, it's 0. And by making this function w of n to be the sum over the chi over the variable I over the tuple and minus 1, then this function can serve as a lower bound problem suit, a lower bound suit. Like if we can find two primes generated in the tuple, then this term will be greater than 0. Like it will be greater than or equal to 1. However, if we cannot, then it's going to be strictly less than or equal to 0, which satisfies the condition that we impose here. Like whenever n is not in the set B, this function is not possible. And if we were to plug this weight into the lower bound suit expression, into this expression, then we will obtain the GPY suit. And here we go. This is the form of the GPY suit. And if we break the weight function, then the task of dealing with the GPY suit is essentially dealing with these two sums that look pretty similar to each other. So the methods of dealing with them are also similar as well. And yeah, this is the form of the sum, and S1 will be the type 1 sum, and S2 is the type 2 sum that is concerned with prime numbers. And making this as greater than 0 implies the existence of prime gaps. So, like to estimate, like we don't calculate exact formula for the sums. We just do estimation. So there are some main terms in the estimation, and then there are error terms. And the treatment for S1, the error terms is easy to control, but in the treatment for S2, we need to consider the distribution of prime numbers in arithmetic progression, because the error terms is in this form. The omega function is the number of distinct prime divisor function that appears in the Selberg tool. And this error term is pretty similar to that form. And the right-hand side, so this 1 over log t quantity, it comes from the prime number theorem. So the prime number theorem in arithmetic progression. Suppose that we are going to calculate the number of prime numbers, a number of primes that are less than x, that are congruent to A modulo Q. Then this quantity will be approximately equal to 1 over order phi of Q multiplied by the integral of 1 over log of t from t equals to 2 to t equals to x. That's the logarithmic integral. And in this situation, we're only estimating the prime satisfying this congruence relationship in the interval x to 2x. And that explains why the integral is going from x to 2x. And we also need to ensure that that A and D are co-prime to each other, or otherwise the arithmetic progression will only produce composite numbers when n is large. And the error terms of the prime number theorem for individual arithmetic progression is easy to control. However, if we sum over those errors together on different arithmetic progressions, that would be a different situation. And we denote this whole error term by the term E, and depends on x because we have an x here, and it also depends on r squared or d, like as in the sum. So the task will be to find some d, such that for every positive integer a, we can find some constant such that this error term, this quantity is less than this constant multiplied by x divided by log of a to log of x to the eighth power. So this error term seems like it is slightly less than x. However, this is good enough for us to apply it to the GPY and to most of the Sieve problems, because like in prime number theorem, like the integral of 2 to x over 1 over log t is approximately x over log of x. So if we can make this log x to any arbitrary large power, large fixed power over there, then it doesn't really affect the main thing. And that's why in Sieve theory, the people like playing with logs. And so here are some results on the estimation of this kind of error terms, because it's not a new thing in the GPY system. It also appeared in other sorts of problems. And the first result concerning this kind of estimation is well-fits. It shows that when d is less than a fixed power of log of x, the error term will be well controlled. And in 1947, Ren Yi, he proved that there's some positive number eta, such that when d equals x to this small positive power, the error term will still be well controlled. And later on, mathematicians, like in between 1947 and 1965, they calculate the specific value for this number. And in 1965, they obtained like the best record up to now, that we can improve this exponent to any number that is less than 1/2. And this will be called the Von-Wierer-Wittenau-Grabe theorem, because that's your name. And they proved the same results on the same year, but they don't really contact each other, so they prove it independently, but their results are quite similar. And that's why it's Von-Wierer-Wittenau-Grabe theorem. And in fact, if we plug in the error terms obtained from Riemann hypothesis, we will obtain something that is quite similar to what Von-Wierer and Wittenau-Grabe did. As a result, when their theorems come out, the theorems are actually applied to prove certain previous results that depend on Riemann hypothesis. Like they can use their result to substitute the dependence of Riemann hypothesis. However, like this 1/2 exponent is not enough, and we also conjecture that it is possible for us to raise the exponent to something like greater than 1/2. So this exponent will be called a level of distribution of prime numbers. So theta is the supremum of the set, such that when d equals x to the power of beta, this error term will be well controlled. So we can, like, this set is bounded above because, like, it is proven that eta cannot be greater than 1. As a result, we have we obtain this sum. We have a supremum, and that supremum will be called a level of distribution of primes. And it's called beta afterwards. And there's a conjecture that's like for any exponents 1 minus epsilon, we can make this error term well controlled. And this, like, so it is conjecture that eta equals to 1. And by the definition of supremum, like any number that is smaller than 1 will actually allow us to make this error term well controlled. So that's the whole idea about this conjecture. And those beta values will be very important in the study of prime gaps. Like in those situations, we don't plug in the specific values of beta, but we so that we can analyze the relationship between the level of distribution and the size of prime gap. And so plugging in this, because we say that beta is the supremum of all these sets. So if we were to like subtract a little epsilon from the beta, then it's going to be an element of this set. And so making r squared equal to this exponent value, like n to the epsilon power of theta minus epsilon, then we can make this then we can make the error term well controlled, and allowing us to give us this estimation here. So this is the estimation of the S1 and S2, the main term. So after performing certain transformation and then dealing with the error terms, making this capital R an appropriate value, we have these two main terms from the GPY. And these are just some arithmetical functions that will be dealt with later. But I will not like show the details of the calculation because it is not relevant to the topic. So to continue calculating the sum, we need to plug in some specific expression for lambda. Like we haven't really so all these steps don't really have relationship with the lambda value. After that, like after this line, we need to look at how lambda affects the value of the GPY. So if we were to record the k-dimensional lambda for Selberg, and if we were to plug in this lambda into the GPY, remember our task is to make s greater than 0 so that we have bounded gaps. But in this situation, even when theta is 1, this is going to be negative because this is less than the denominator and this is less than 1, so this whole thing is less than 3. So plugging in this k-dimensional Selberg sieve does not allow us to produce infinitely many, does not allow us to produce the bounded gaps between primes. So like one may consider that, well, the whole method is a failure. However, GPY did not give up. They slightly modified the dimension of this lambda. Although the problem, the sieve question is a k-dimensional problem, we don't have to attack this problem by following the guideline using the k-dimensional sieve. Like there isn't really a strict rule for that, and we don't really know that this is just the optimal version of the lambda that can be plugged into the GPY sieve.
This number,
yeah, because like, yeah, they are asymptotic, but if we plug this in, we obtain something that is asymptotic to that specific expression.
again, we just,
Yeah, we just plug in this and it will be an approximation to something that is seemingly optimal.
okay.
So yeah, k-dimensional lambda cannot handle a k-dimensional problem. So we can cheat a little bit. Why not consider a lambda of higher dimension? And here's the dimensionality augmentation attack. So basically what GPY these people did is that they increased the dimension of lambda to k plus L, and L is some number to be determined later. Applying this modification, they obtain a new asymptotic expression for S. And this is the part, this part is the coefficient. And because if we make k and L goes to infinity in the sense that L grows slower than k, then this function will go to 2. The function on the right hand side, this function will go to 2. Like we first make k go to infinity, so these two terms become 1. And then we make L goes to infinity, so when we have 2. So this limit tells us that for any epsilon greater than 0, we can choose k and L such that this quantity is greater than 2 minus epsilon. Like because the limit is 2, we can choose some k and L values to make this greater than 2 minus epsilon. So 2 minus epsilon multiplied by theta and then minus 1. If theta is greater than 1/2, like suppose it is 1/2 plus some delta, then we can make epsilon small enough such that this 2 minus epsilon times the 1/2 plus delta is greater than 1. Like this is possible. And then with this in mind, we can make this whole thing greater than 0. This indicates that when n is sufficiently large, the left-hand side, the s term, will be positive. And this will allow us to produce bounded gaps between primes. And like we can choose some k, and then if we can locate a tuple that h1 to hk, that integer tuple for this given k, then this quantity greater than 0 will imply the existence of bounded gaps. And we're going to construct a like an admissible tuple that is suitable to this given thing. And the necessary condition for all these miracles to happen is that theta is greater than 1/2. But our current technology is like theta equals to 1/2, so we need to keep that in mind as well.
So is this sequence
Yeah, theta is the supremum of the set. Yeah, theta. Yeah, supremum of the set of the theta elements.
And then we check the k is the dimension, k dimension p. Is the k same as the k in people?
I got to what to do.
You see that S is the k dimension c, right? Like k here. Is the k same k as the tuple?
Yes, so that's the same.
The same k, right?
Yeah, it's the same because like we're like this polynomial is a k degree polynomial.
Right.
Yeah, and the dimension comes from here.
Okay.
So we are now like in the previous slide we are playing with the k dimensional system. Now we are attacking the problem using k plus l dimensional system. And the result is that if we can make this theta greater than 1/2, then we can make this s greater than 0. And if we can find an admissible tuple with exactly k elements, then all of these results allows us to conclude the existence of bounded gaps between primes. So let's see. So to construct such an admissible tuple, and we do need to keep in mind that like there's not like a unique tuple for that. Like we can find many tuples that are admissible and also have exactly k elements. And this is just one construction that is quite loose, but they are useful because it tells us that we can actually find a tuple for this given k. And the approach is that we choose h1 up to hk. We will make them certain prime numbers that are greater than k. Why greater than k? This is because for any prime number greater than k, the number of solutions to the congruence equation Qn equals to 0 is going to produce at most k roots. And because p is greater than k, so the number of roots will not be equal to 2. And so that's the case for like p greater than k. And when p is less than or equal to k, we can analyze the case separately. Because if we plug in n equals to 0 into the expression, we see that whenever p is not a prime greater than k, it will not divide all those primes because those are the prime numbers that are greater than k. Certainly not divisible by a number less than or equal to. And these two conditions allow us to ensure that like this construction allows us to make h1 up to hk forming a admissible couple. And the conclusion is that, like, because if theta is greater than 2, greater than 1/2, we can choose some k to make this quantity greater than 0. And this k, which depends on theta, also allows us to choose an admissible couple. And this admissible couple is going to allow us to produce an upper bound for the prime for the bounded gaps between prime. And putting everything together, we obtain GPY theorem, which states that if the level of distribution of prime numbers is greater than 1/2, then there exists some constant which depends on theta, such that the limit infimum of the prime gap function is less than or equal to this constant. So the next question is that, is it conditional result? Can we make this unconditional? And that part will be that part follows from the word from Yitang. And that's a brief introduction to his experience. He had this PhD at Purdue in 1991, and due to certain conflicts, his advisor refused to write him a recommendation letter, and which indicates that he will have a hard time finding a job in the academic job market. And so in the 1990s, he actually worked a few years in a Subway sandwich shop before becoming a lecturer at the University of Hampshire, 1999. And in 2013, he proved this unconditional result that the prime gap, the gaps between consecutive primes, is less than 70 million, infinitely many times, which just makes what GPY is like unconditional. And after that, he became a professor at UC Santa Barbara. And Zhang's methods like consists of a concept called a smooth number. By smooth, it means that this number does not have large prime diversity. So in the Sieve situation, we want those integers to have only large prime diversity. But in this situation, we only want them to have small prime diversity. And in GPY situation, lambda d equals to 0 when d is large. And in Zhang's situation, lambda d equals to 0, not only when d itself is large, but also when d has some prime divisors that are large, like greater than n to certain powers. And as a result, in Zhang's setup of the GPY sieve, like it is quite similar to the original sieve. Like in GPY sieve, these purple ones, so these purple attributions are not included, but in Zhang's sieve, he adds these conditions to the sum over lambda. And that's just the whole thing presented together. And the only difference between this and the original sieve is just these purple conditions.
So what do you mean by P divided?
P divides D implies P is less than or equal to D, which means that when P is greater than D, P will not divide D. And which means that D does not have prime divisors that are greater than D.
Oh, right.
So D is a Z smooth number. So you might imagine that because we modify the conditions of the sieve, then it is likely that we need to do a whole lot of calculations again. But what Zhang find out is that adding these conditions do not really change the main terms significantly. And by main term, I mean the T1 and T2 on the right-hand side, okay, from these estimation of the original GPY sieve. So if we just estimate the differences between those terms, like between the main term from S1 and S2 in Zhang's sieve, then it is likely that they are not different too much they're not like so different from each other. And these are just some details of this calculation. And using those numbers, it shows that the main term in Zhang's sieve, like for the type 1 sum, for this type 1 sum, the main term is slightly greater than than GPY's main term. And the sum over the primes, the prime numbers, the type 2 sum in Zhang's sieve It's just slightly less than the actual prime sum, actual type 2 sum in the GPYC. So they're quite close to each other. This indicates that like Zhang does not have to spend a few 20 pages to calculate the actual asymptotic formula for T1 and T2 for the smoothened sieve. However, he spent 20 pages on obtaining this. So if he had to calculate the actual expression for these two terms, then it's going to be take more than 50 pages. The structure is more complicated than the original one. And so we might have a question. So since they are so similar, why do we even bother putting this purple thing into the expression? And the answer is that there's significant difference when we were to estimate the error terms emerging in the treatments of these expressions. In GPY, the error terms also have a similar form. However, it doesn't really have this purple condition. And this condition actually allows us to sum less integers than the error terms in the GPY. So in GPY, the error terms is summing over more individual errors. However, in Zhang's sieve, we are summing a smaller amount of them, which means that it is possible that we can play certain tricks to deal with the error terms of this form. And the error terms in the GPY sieve, the theta value for that, we only have 1/2 for that error term. But in Zhang's situation, he applies certain results from arithmetic algebraic geometry. He namely the links proof of the Pintz conjectures. So using this result, he proved that if we make R to be like R squared to be the n to the 1/2 plus 2 times this symbol. This is a variant of the pi symbol. And this is quote from his paper, he used the symbol for that. So if R is equal to n to the 1/4 plus pi's power, which means that R squared is n to the 1/2 plus 2 pi power, then we see that the error term in Zhang's sieve is well controlled. And because squaring this gives an exponent that is slightly greater than 1/2. And because Zhang's sieve well approximates the original GPY sieve, which means that the theta value in this Zhang's smooth case can be extended to something that's beyond the 1/2 barrier. And in GPY theorem, we show that if we can extend beyond, if this term is removed and we can make theta greater than 1/2, then we have bounded gaps. But in Zhang's situation, plugging this R gives a kind of theta that is greater than 1/2, which indicates that, well, we have the bounded gaps between terms. And now let's see how we can obtain that. So this is the final estimation in Zhang's version of the GPY sieve. As you can see, the C3, in GPY sieve, here's C2 of K times theta. But in Zhang's situation, we have a more complicated expression. And by plugging in, so this is a numerical calculation. There's not many wisdom in it, but just plugging these values, Zhang found out that this C3, the sum, is strictly greater than 1, which makes this S term greater than 0. And we can find and this K allows us to make this sum greater than 0. Which means that as long as we can find an admissible tuple with this number of elements, then we have the bounded gaps between primes. And up to now, we already established that the prime gap is bounded infinitely many times. But Zhang can proceed from this further, that we can obtain an actual upper bound. We can use this thing to obtain that 70 million bound.
Why is it multiple times?
Yeah, because I need to analyze this because it's not just multiplying this term by 20. It actually uses a numerical version of the prime number theorem. And this version looks like this. So for when x is greater than 60, and in the case we are discounting something like more than 10 to the 6th power, so we can just use it inequality. So when x is greater than 60, we can find this, we have this inequality for the prime counting part, which also certainly implies the prime number theorem. And when k is 3.5 to the 10 times 10 to the 6th power, we need to find a couple so that we can find k prime numbers greater than this k to form an admissible couple. And we want to know the distance between the k, like k, this is k, and this is h1, h2, and then up to hk. And this distance, like the distance between h1 and hk, will be the upper bound for the prime gaps. So our task will be to find a m such that the interval consists from k to n has more than k primes. And then this number m will serve as an upper bound for the prime gap. And by just plugging in the inequalities, like the final thing looks like that. And using computer cannot count primes directly, but calculating a logarithm is a much easier task. And numerical verification shows us that if we just set m to be this large number, then the right-hand side is going to be greater than k. And that's where the 70 million came from. It's loose, but it's finite, and that's enough for us. And so this is the result on Yitang's paper, that we can bound the gap between consecutive primes by 70 million for infinitely many times. And so this is Zhang's theorem. And even in his paper, Zhang said that the result is, of course, not optimal. And however, he is not interested in optimizing this result. He just said replacing the right-hand side of that inequality by some smaller value is an over problem that will not be discussed in this paper. And Zhang also moved to some other area of mathematics, other area of number theory after publishing this research work. So after Zhang, this project, Polymath 8 project, because Polymath project, there are many of them to deal with different problems. And by the time Zhang published his work, it became the 8th one. And so this project is there's a group of mathematicians working on it, including Terence Tao. And this project was initiated to improve Zhang's result. And by November 2013, the 70 million is reduced to something that is greater than 4,000, which is really remarkable compared to the initial one. But can we make this even better? Can we improve it to few hundreds? That is still a question. And remember, this result is in November. And James Maynard's one is in December. His paper was published soon after this one. So I think this introduce James Maynard. So we mentioned that Zhang Yitang published his paper, he announced his result in 2013. And James Maynard was still a PhD student back then. So he actually started working on the prime gaps when he was when he was just a PhD student. And then by the time he finished his paper, he became a top postdoc. So he's actually doing this research in a transitional phase. So in December, James Maynard proves that we can improve this for something, this 4,000 thing into 600. And he also proved a generalization that we can, for every m, we can find some constant that depends on m, such that find a constant that depends on m, that we can make m plus 1 consecutive times bounded into that interval, bounded by this number. So the gaps between, so this is called the bounded gaps between many primes.
Isn't that similar to the one by the K one mentioned with conjecture?
Yes, you are talking about the relationship between m and k. So James Maynard's result actually implies that like as long as m is just smaller than certain function of k, then we have value like m primes of this k couple. So he's basically like generalizing, like we have a k couple and we want to say that we can generate like m primes inside. We have bounded gaps between many. And this significant contribution allowed him to receive fields medal like this year, few months ago, And let's see how Maynard attacked this problem. In the GPY sieve and Zhang's sieve, this term is just lambda d, a single variable function. And somehow, just because of that function is a single variable function, we can only produce bounded gaps when we make the beta greater than 1/2. However, in James Maynard's situation, he is not increasing the dimension of lambda. He is actually reducing it. How does he reduce it? This problem is a k-dimensional problem. James Maynard is attacking it by splitting them into k one-dimensional problems. So he is applying a k sieve together to deal with this problem. So like back then, like there's an enemy and you just send one soldier to send one soldier with strong equivalents to defeat the enemy. And now James Maynard is sending multiple soldiers there. So it's a much different situation and more flexible situation. This allows him to obtain the 600 now. Better than Holy Math project, better than Zhang Yitang, that theta equals 1/2 implies around 600. And also this bound that bounded the gap between like many times. So this is a summary of this result. And I'm currently actually still reading the proofs of some articles of this paper like a few days ago, even like yesterday. And so by choosing this lambda carefully with like some more monstrous expression than the lambda d we had in Selberg, you obtain a lower bound for this modified sieve, such that this is just a positive term, and this is since this is an integral over f squared, it's also non-negative, and we choose f properly so that this is positive as well. So we don't really need to worry about this part. So the important one part is also this. And this expression is quite similar to the C2 times theta expression in the GPY sieve. So there are some similarities. But this term is just quite different from the original GPY sieve. And MK is just a ratio of K times J divided by I. So these are some multiple integrals. And these integrals, like if you integrate a function in some fixed region, then it's giving you a number. So this mapping, this M mapping, it sends a function to a real number. And in the calculus, in the language of calculus of variation, this is a function, so a massive function to a number. And to optimize this functional, like the problem optimizing this functional, is a variational problem. So let's have an overview of James Maynard's work. Like he transformed this number theoretic prime problems about prime numbers into a deep variational problem in mathematical analysis. And that's why this field is called analytic number theory, because like we are using problems for tools for mathematical analysis to analyze problems concerning time. So he chose this function f carefully, such that when m is optimal, it is greater than some increasing function of k. And this is where, and this indicates like when k goes to infinity, this quantity is going to be positive infinity. Why is it important? It is important because like remember that we have the row term here, and this row term is also the same here. Like in the GPY sieve, when rho equals to 1, we can have bounded gap between two consecutive primes. And when rho is like some larger number, then it is going to produce bounded gap between rho plus 1 consecutive prime. And So MK is increasing, indicates that we can choose some arbitrarily large goal, such as we can choose some K couple to like make this quantity a positive number. This effectively shows us that there is a bounded gaps between many primes, and that many is just any fixed positive integer, and we have a bounded gaps that can split these many primes into a fixed interval. So this is how James Maynard proved this generalization. And to put this formally, there is a Harvard constant phi that depends on m, such that p of m plus m minus pn is less than this constant infinitely many times. Which is like, even when theta equals 1/2 is assumed, we can still have this generalization. So Maynard's method is like a boosting, like a boost towards the study of prime gaps. It's very different from Zhang's method, but it is also very extensive and can be generalized in slightly different problems. So we have proven the generalization, and now we can see how we can improve that 70 million, that 4,000 down to 600. The way is that because we are supposed to find theta over 2 multiplied by this m term greater than rho. And in the consecutive 2 prime case, we just need rho equals 1, which means that as long as we can choose some k to make this inequality come true, then we can locate a admissible tuple with k elements to give the upper bound for the prime gap, for the small gaps. And when theta equals to 1/2, the right hand side is transformed to 4. And James Maynard by something like complicated calculation finds that when k equals to 105, this quantity is going to be greater than 4. And then he also uses some computations by other mathematicians that this value of h is the optimal admissible tuple. By optimal, I mean that the largest distance between 2 elements are the smallest in this couple. And in this couple, he finds that the maximal distance, because they are sorted from these two, from minimum to maximum. So this, the gap between the largest gap between all the elements here is exactly 600. And this is why James Maynard is able to remove down to 600. And he improves it without modifying the values of theta. And because up to the end, James Maynard did not plug in the values of theta. So if theta is improved in the future, he can just replace the theta with the larger value and then calculate a different k to obtain a better value. So that's everything about today's talk, and there are also some further improvements after James Maynard. So the polymath project before James Maynard is called the polymath 8. And because this improvement, this polymath project after James Maynard is still concerned with prime gaps. As a result, this new project is just polymath 8 letter B project, and the previous one is just 8 letter A. So these are 2 projects, and the project after Maynard is called the bounded gap between many primes, and the project before Maynard is the bounded gaps between. And so this is the current record. The bounded gap between the small gaps between consecutive primes is less than or equal to 246 infinitely many times. That's the current record for bounded gaps between 2 primes. And the bounded gaps between many primes. James Maynard actually has a explicit expression for that C of that. He proves that there's some absolute constant. He didn't show what it is, but he showed that there is an absolute constant for that, and then multiply by some increasing function of n. So he has this bound for the gaps between many primes. And polymath 8b project improves this, like the new one replaces m to the 3rd power to m to the 1 power, and then also makes this 4 to reduce to some smaller number. And this is currently the best record, and I don't really hear about any further improvement than this. And this was like in 2015. So, and these are some of the works cited in this talk. And thanks everyone for it. Yeah, any questions? This is the Q&A section of the talk.
How does all of this, because I remember in the beginning you said that the main influence of n plus 1 and 2.
So like we have the inequalities here.
Yeah.
Like back like before everything we have like we don't even know whether it is less than a finite, whether it is finite or not. So Zhang proved that this is a finite number. And he also proved that this finite number will be less than a large but fixed number, namely 70 million. And later on, this number is pushed to some smaller and smaller number. And the destination will be 2. So if we can just push to 2 from the above, and because from elementary argument, we know that this quantity is greater than or equal to 2. So if we can push this down from above back to 2, then we have the 2 prime conjecture.
But like, you think it's 2. But
yeah, but we just want to improve this. Yeah. And yeah, so this is like a hardcore approach. And there's also like an approximate version for that. It is proven by Chen Jingrun when he proved the approximation to Goldstein's conjecture that every integer, every large even integer is sum of a prime and a product of at most 2 primes. There's a similar result, like because the arguments for proving both of them are so similar that Chen Jingrun in the last section of this paper said that the similar result in twin primes, like they're so similar, so I don't want to prove it again. So that result is there are infinitely many prime numbers, P, such that P plus 2 is either a prime or a product of 2 primes. And that P plus 2, we can actually generalize that. For any fixed integer K, there exists infinitely many primes, such that P plus 2K is either a prime or a product of 2 primes. So that is a older way of approximating twin prime conjecture. But this is the modern approach. And currently we are on like 246. And regarding this result, there's also like another story because that explains why I even entered this field. It was like last December. There's a professor at Shanghai Jiaotong University. He announced like he believed that he improved this 246 bound to like something like 160. So he announced this result and gave a talk about the method. But back then I was still studying the Goldstein's problem, so I don't really know anything about prime gaps. As a result, I just listened to his talk and he mentioned, however, most importantly, he mentioned this lower bound problem. He mentioned this GPY criterion. And I think that is very interesting because it connects to some Selberg suit, which is also important in Goldstein's problem. So due to this connection, I planned that I should begin studying this prime gaps problem. And after the talk, and he also his result, his paper is still under review because he also even modified multiple versions on archive. So people really don't trust his paper because like even if the paper is like put on archive, and you see that there are more than 12 modifications on this. It's like version 12, version 13, then like I just can't believe that this is a true result because he has so many modifications. As a result, like there's no any big news coming out in social media. However, like so because like in December, like that was when I was still like sending out application for university. So I think, well, maybe I should pay more attention to that one instead. And as a result, I started learning about all these like in July, like in late June and July, I started learning about these problems concerning the prime gaps. And we can see from this list. So it was like in June, I kind of studied about this, and then later on, like it was like it takes only less than 2 weeks for me to get here. And then John's paper took me like 3 or 4 weeks on that. And James Maynard, I'm currently reading that. And on the last weekend, I managed to read the first half and the second half. Like the first half of the James Maynard's paper is dedicated to proving that integral expression. So this is the first half of James Maynard's paper. And the second, so this part is more of like arithmetical nature. But the second part is more of like analysis, like calculus of variation. These parts I'm still like reading about. And he even need to introduce some physics heuristics to choose the function f. Like f squared is non-negative, so we can interpret this integral as like calculating a mass over a certain object, certain high-dimensional object, and this is the density function. And so if we just interpret it as mass, he introduced something like center of mass into it. But I'm still reading that, but I think this is like quite amazing. Yeah. So yeah, that's about me.